So now we are going ahead with the discussion on the optical properties of the biomolecules. So this is if you want to do some self-rating, you can go to Leringer's page this to this, and you can do some self-rating. So the next thing that would come logically to optically active molecules is the DL nomenclature. So DL, what are DL nomenclature? So to understand that, you have to first put the amino acids or any biomolecule in the Fisher projection. So Fisher projection means COOH on the top, CH3 on the bottom, and NH2 and H in the vertical on the horizontal position. So this is how another example. So this is for alanine, and this is for cysteine. Okay, this would be the DL nomenclature. So, and this at this position, what you have to do, if between the horizontal positions, so there should be H and NH2. Okay, so the rule here is that the most oxidized carbon should be on the top and the least oxidized on the bottom. So most oxidized means here the COOH, and here the least oxidized is the CH3. Most oxidized COOH, least oxidized is this carbon here. This is usually the side chain. When you have the carbohydrates, most oxidized is the carbonyl group, least oxidized is the alcohol. Okay, CH2OH group. So this is the CH2OH as part of the alcohol, right? So similarly, another molecule, most oxidized on top, the carbonyl, and the alcohol CH2OH at the bottom. Okay, so that should be the preferred arrangement in terms of the Fisher projection before we go ahead and learn the DL nomenclature. So once your molecules are in this position or in this projection, so you have to consider the penultimate carbon. That is, this is the last carbon that is in the chain, and this being the penultimate carbon. Okay, ultimate means the last, and penultimate mean the one before that. Okay, so in this position, if between the horizontal residues, if the H is on the right, that is on the right side, this is an L. If the H is on the left, that would be a D. Okay, this case the penultimate carbon is this one. So this is the last carbon, ultimate carbon, this is the penultimate carbon. So what would be the configuration here? The H is on the left side, so this should be a D, and in this case the H is on the left side on the penultimate carbon. This is the ultimate carbon, this is the penultimate carbon, which is on the left side, so this is also D. Okay, so if I have to consider another molecule, say I do it on here. Okay, so I'm going to draw glucose. So CHO is the most oxidized carbon, CH2OH is the least oxidized carbon. Okay, so H, OH, H, OH, OH, H, OH, H. Okay, so I'll try to reversing on the last one. Okay, and draw it again. So OH on H on reverse position. So the H here is on the right side, so this must be L. So if what I will do for the same molecule, I will simply draw its diastereomer, meaning that I will keep everything the same, and I will reverse that carbon only, the penultimate carbon. Okay, all the first three positions I am keeping them identical, and I'm simply reversing the position of this carbon. So H is on the left side now. Okay, so it is becoming a D. Okay, so that is the difference. Okay, the diastereomers, simply because this carbon, the penultimate carbon got changed, or the stereochemistry of the penultimate carbon got reversed, so it became D2L. Okay, so that is that. So this is a DL nomenclature. So why do we learn this? So amino acid structure, if you write them in a Fisher projection, all naturally occurring amino acids are L. Okay, so if you, this is the most oxidized carbon side chain, so the H is on the right side, so meaning this is L. So most of the amino acids have only one optically active position or one chiral center. Okay, so if you reverse this position, this becomes its enantiomers. Okay, because of the imaginary mirror plane right here, and this molecule now the H is on the left side, so meaning this is a D. Okay, so that is that. So enantiomers, so this is a D enantiomer of the same amino acid. So as I said, all naturally occurring amino acids, they are L. Okay, so there are different theories on why that is, so which you can discuss in the actual class, but this is a fact. Okay, so regardless of what side chain you have, because you see, while doing the D and L, you are not really considering the side chain. You are just considering the position of the H and the NH2 group, because COH, the most oxidized carbon, is always on the top, right? So that is the DLL nomenclature of the naturally occurring amino acids. Okay, meaning their positions in terms of the 3D space, regardless of whatever your amino acid is always fixed. Okay, so let's put this in our mind, that they are always in this configuration. They are always is in L configuration. So one follow-up thing that I would like to discuss before we move ahead to the proteins is the hydrophilicity and hydrophobicity. So hydrophilicity and hydrophobicity briefly touched upon when we discussed the TLC lab. So hydrophilicity, as the name suggests, is that it loves water. Okay, so hydro means water. Okay, hydro means water, and phil means like. Okay, so this means water and phil means like. So it likes water. So those which does not like water is called hydrophobicity. So you can look up amino acid structures and you can tell from the structure of the side chains that if something is hydrophobic or not. Okay, so if you have groups that have parts charge separation or any charge like complete full charge like plus or minus, they would come from electronegative difference in the atom, so those would be hydrophilic. So why they would be hydrophilic? Because water also has a prominent charge separation, the water being delta minus and this is delta plus, this is delta plus. So they like to interact with water due to dipole-dipole interaction or electrostatic interactions. So groups, what kind of groups would be there? So for example, if it is OH, CO minus, NH2, NH3 plus, so this loves to interact with water due to their polar character. Okay, so these molecules will, see, if they are present in a surface or in a molecule and this is water, the water will spread around and try to interact with it. Okay, due to dipole-dipole interactions. The groups that don't like to do it are those that do not have any or low charge separation. So predominantly groups like aromatic groups, okay, CH3 groups, CH2, CH3 groups, because their electronegativity difference between C and H is quite small. Okay, so this is 2.5 and 2.1, so they do not generate a lot of charge. If it's carbon and carbon, then there is no charge altogether. Okay, so these are hydrophobic because they do not like to interact with the water, because water has polar character and these groups do not. Okay, so this would be form hydrophobic. So in case the water, when if there is a surface and these groups are present, the water will try to repel away from the surface. Okay, so what is the manifestation of that? So if you try to draw an angle, a contact angle along the, and draw a tangent of the water surface on the surface of the solid surface, so this is what it's going to look like, and this angle for the hydrophilic surface would be less than 90 degree. Same if you draw a tangent of the liquid solid surface and this is the and if you draw a slope on the surface, this is going to be more than 90 degree. Okay, so that is how it's gonna make a difference. Okay, so this particular angle is called contact angle, and just to summarize, that contact angles are less than 90 degree when it's a hydrophilic surface, and when it's hydrophobic it is more than 90 degree. So what are the hydrophilic and hydrophobic amino acids? So that you can identify with respect to the side chains. Okay, so remember, we are not considering the NH2 and the COOH here, just considering the side chains, that is this groups or this groups right here, but not NH2 and COOH, because they will form part of the protein backbone, so their properties are irrelevant in determining the side chain, in terms of determining the hydrophobicity. Okay, so look at this following amino acids, and you can look up their side chains. So these side chains have predominantly made up of CH and CC groups. Okay, predominantly made up of CH and CC groups. Okay, so these are predominantly hydrophobic side chains, and they would repel the water. So these two are somewhat less hydrophobic because they have a little bit of polar character from the NH and the COH, but they are still hydrophobic. These ones are quite hydrophobic. Also, one more thing you can tell is that you can, depending on the extent of the CH and the CC groups present, you can also classify them on how hydrophobic they are. So you can tell easily that isoleucine would be more hydrophobic than alanine. Leucine and isoleucine, they are probably identical. Okay, valine is somewhat less hydrophobic than leucine because the number of CC and CH groups are less. Okay, so that is something you can also classify. Let's look at the hydrophilic amino acids. So hydrophilic amino acids have some kind of polar groups on their side chains. So for example, asparagine, there is NH and CO. Okay, there is NH and CO. Okay, cysteine, SCS groups are there, or SH groups are there. Glutamine, NH and CO. Okay, methionine is not so much, but still sulfur is there. Serine, C and O. Okay, threonine again, OH and CaOH. Okay, these groups, the acidic side chain and the alkali basic side chains, they actually have electrically charged side chains. So meaning at natural pH, this would become CO minus, this COOH. Okay, so this is like quite hydrophilic. Similarly, glutamic acid also will become CO minus at pH 7. So this is also quite hydrophilic. The arginines, they would become NH3 plus at the pH 7. So that would also become polar, very polar. This would also become NH plus and would become highly polar. Lysine will become NH3 plus and will become highly polar. So these are all hydrophilic side chains. So let's just discuss something, that how amino acids form protein. So this forms through peptide or amide bonds. So let's give an example of that. So let's say you have an amino acid which is R, NH2 and COH. Okay, so this is the alpha amino, this is alpha COH, and there this is reacting with another amino acid, NH2 R1 COOH, which is reacting with another amino acid, NH2 R2 COOH, which is reacting with another amino acid, NH2 R3 COOH. Okay, and let's see what happens. So how they are forming the protein. So an easy way to tell is that by removal of the water. So you can see, if you take away one OH from here and one H from here, one OH from here and one of the H from here, one OH from here, one H from here, okay, and minus 3 H2O, because there are 3 H2O that would be lost. The product is going to look like this: NH2 R side chain CONH, R1 CONH, R2 CONH, R3 COOH. Okay, so we originally had 4 amino acids, because you can see there are 4 side chains here, and the product also has 4 amino acids because of the 4 side chains here. And so if I want to put the original side chains in this chain, so this was 1, okay, and this particular one is right here. Okay, so then I put the next one, that would be this particular one right here, and that is this one right here. Okay, then I put the next one, which is, let's say, this one right here, and that would be this one right over here, and then followed by the last one, that would be this one right here, which is right here. Okay, so one thing that you should look at is that the backbone, which is the alpha amino, alpha carbon, and alpha COH, is being repeated. Alpha amino, alpha carbon, alpha COH, alpha amino, alpha carbon, alpha COH, alpha amino, alpha carbon, alpha COH. Okay, alpha amino, alpha carbon, alpha COH. So they are being repeated. So one thing you can tell, that this is a biopolymer because this has a repeating unit. Okay. Second thing you can make out is that regardless of the backbone, the original NH2 and COH is no longer present. Okay, so they are part of the backbone now. So what is going to make a difference, the property of the peptide, is the R groups. Okay, so R groups is what defines the property of the peptide or protein. Third thing you can make out is that number of amino acids you can tell by the number of side chains. Okay, so how so? We just discussed this. So you can see there are 4 side chains, so there must be 4 amino acids present. The second thing is the presence of the peptide bond. So this particular bond is called the peptide bond and amide bond, the one connecting the 2 subunits. Peptide bond or the amido bond. Peptide bond or the amido bond. Okay, so that is peptide or amide bond. Okay. Fourth thing that I did not mention, fifth thing I did not mention, but implicitly present, is that when you draw a peptide structure, the amino should be on the left and the COH should be on the right side. So this is when you are writing a peptide formula also, that a peptide chain should start from amino or N-terminal, N being the nitrogen for the amino, on left side, and COH or the C-terminal on the right side. Okay, so that is the key things. Okay, so this is where I will stop this lecture, and we'll cover it take it up from here itself.